have any choice in the creation of the universe. What he meant was, are the laws of physics immutable? If you change one thing a little bit, does the whole structure collapse? Is there only one set of laws of physics, or could you have an infinite number of laws of physics, and anything would work? And that's the question we want to know. And if the anthropic principle is true, there can be an infinite set of laws of physics, and we just measure the cosmological constant that the value it has because we're here today. Now, particle physicists have jumped on this. Because see, particle physics is way ahead of cosmology. Cosmologists haven't understood one big number. But particle physicists haven't understood much more for much longer. We haven't understood why gravity is the weakest force in nature. We haven't understood why the proton is 2,000 times heavier than the electron. We haven't understood why there are 3 generations of elementary particles. We understood anything. So maybe they said, this is great. Maybe we don't have to understand anything. Maybe it's all an accident. Maybe instead of a theory of everything, we just need a theory of anything. Well, we have such a theory. It's called string theory. For those of you who don't know about string theory, this is my one slide summary of string theory. One physicist said to another, I just had an awesome idea. Suppose all matter energy is made of tiny vibrating strings. And the second person says, wow, what would that involve? And the first person says, I don't know. So that's the history of string theory over the last 40 years. But in fact, what it's predicted, if anything, is that the universe, unfortunately, depressed the string theorists, because the string theorists need extra dimensions in string theory, 7 of them on average, and they have to get compactified, and so there's only 3 large dimensions, and every different way they can compactify produces a different universe. So it turns out string theory doesn't, if anything, doesn't predict a single universe, it predicts an infinite number of possible universes, and that used to be a bad thing. But all the words become beauty marks in string theory, and now they say, look, that's a great thing, we predict any possible universe. So we're right. In particular, in every different way of compactifying these extra dimensions, you might produce a different energy of empty space, and we'll find the one we live in because it's the one we can live in. Now this is, whether this is science, I don't know. If it is, it's bad news. But it's worse. Well, George Bush jokes are too cheap. I'll think I'll skip that. Let me just go to the future. Because really, what the really worst thing about all this cosmological constant is it predicts a future that really, well, you can decide whether you like it or not. The first philosopher to point this out was Yogi Berra, who said the future ain't what it used to be. And here's what he meant by this. George Orwell said, to see what is in front of one's nose requires a constant struggle. And what did he mean by this? Well, clearly he meant this. He meant that in a cosmological constant dominated universe, turns out the energy of empty space is a constant. What that means is the universe begins to expand exponentially. But what it really means is that the velocity of objects, and this is what, if this is distance, and put a little dot above it, it means velocity in physics. The velocity of objects is proportional to distance, the Hubble constant. It's here, but it's a constant of time. And that means if the distance is big enough, then the velocity is bigger than the speed of light. Objects farther away from us than a given distance are moving away from us faster than the speed of light. Now, this should be impossible. But it's not, because you have to be like a lawyer and parse this a little more carefully. Einstein didn't say that's impossible. What he said is nothing can travel through space faster than the speed of light. But space itself can do whatever the hell it wants. General relativity. And space can carry things away from us faster than the speed of light. In fact, in an expanded universe, you can be moving at the speed of light and still be standing still. You're doing it right now, depending on how much coffee you had. We're not moving very fast with respect to each other, but a galaxy that's stuck in a lecture, or an audience in a galaxy that's stuck in a lecture at the other end of the visible universe, they're hanging out there, and we're hanging here. We're not moving very fast. They're not moving very fast, but they're moving away from us at the speed of light, and we're moving away from them at the speed of light. How's that possible? We're at rest, and they're at rest, but the space between us is expanding. And so in general relativity, objects greater than a certain distance away from us are actually moving away from us faster than the speed of light. And it's worse. If the universe is accelerating, more and more objects are going to be moving away from us from the speed of light, and they're going to start disappearing. We can ask when that's going to start to happen. If you plug in the numbers, it's going to start to happen when the universe is 18 billion years old. Not too far in the future. Okay? because I want to talk about what the future universe, to conclude the last 3 or 4 minutes, what the future universe will look like. Because I think it gives us some perspective that should humble us. Not a word that's often used associated with me. But should be. Because we should be humble about the fact of what we know. Because let's remember how we began this lecture. Okay, with the universe around 1900, the universe was static and eternal. And in fact, a guy named Sitter wrote down a metric for general relativity that described the static and eternal universe. We now know the universe isn't static and eternal. What will be the case in the far future? What will be the case on planets around stars in the far future where astronomers come up and they try and measure the universe? What will they discover? Well, they'll discover the universe that thought we lived in 100 years ago. Because the only thing they'll see is the Milky Way galaxy. Or a bunch of our galaxies will come together and merge in a few tens of billion years, make one big galaxy. Why? Because all the other galaxies in the universe will have disappeared. They'll all be moving away faster than the speed of light. So if you think about all of the bits of data that tell us there really was a Big Bang, they all disappeared. The Hubble expansion disappears because there are no galaxies anymore. You can't see the tracers of the expansion. And it's even worse. We've discovered dark energy, but all evidence for dark energy will disappear. In fact, at that time, it turns out when the universe is about 100 billion years old, spacing long, except maybe compared to this lecture, there'll still be stars around, like our sun, and planets around those stars, and astronomers that are powered by solar power and all the rest. But the energy of matter compared to the energy of empty space will not be 1/3, it'll be 1 part in a million billion. The energy of empty space will be the dominant stuff in the universe, but there'll be no way to measure it. Because the only way we can measure it is by looking at galaxies and the expansion rate of the universe, but the galaxies will have gone away. It turns out there's only one time to measure the dark energy. That's today. At all earlier times, it will be invisible. At all later times, it will be invisible. So we don't know about the Hubble expansion. We don't know about the dark energy in the far future. Well, what about the cosmic microwave background? That'll tell us there was a Big Bang. No, it disappears. Because as the universe expands, the microwave background frequency will go down, its intensity will go down, but that doesn't matter. It turns out in our galaxy, there are things called free electrons. We know their density. Doesn't really matter. That means our galaxy is a plasma. There are charged particles in our galaxy, and radiation below a certain frequency can't make it into our galaxy. And when the universe is 50 times its present age, none of the cosmic microwave background will be able to get into our galaxy. So observers in the far future will not measure the expansion rate of the universe. They'll not see the universe expanding. They'll not know there was a Big Bang because they won't be able to measure the microwave background. They'll see our galaxy being a single island galaxy in an empty universe, static and eternal. So the picture of the future will be a return to the wrong picture. Falsifiable science will come up with completely a false answer. I mean, they'll discover general relativity, they'll discover electromagnetism, they'll discover quantum mechanics. They'll do all that. They'll build telescopes and they'll come up with exactly the wrong answer. So that should humble us, because we've discovered this universe that's really weird. We don't understand any of it, but maybe if we lived 5 billion years ago, we would have seen something that would give us a different picture. Maybe 100 billion years from now, there'll be an observable we can't measure now that will change that picture. We shouldn't be so certain we have all the knowledge right now. And the good news, which I'm an optimist, as you can tell, I want to leave you with 2 bits of good news. First of all, we live